Hello everyone, welcome to my channel. Now I will check how to prove some useful results of probability theory. That says we need to put some results put into supplement 4. Well, so the first result talking about if we have xi follows binomial distribution with the parameter n sub I but common parameter p, and then sum of the binomial distribution it should follows binomial again with a common parameter p. So this is the first result. Of course, we have the assumption all the variables here, they are independent random variables. And the second one, we talk about binomial, negative binomial distribution with the parameter alpha sub I and the common parameter p again. Likewise, some of the random variables here. It follows negative binomial again with the sum of alpha sub I and the common parameter p. And next one is Poisson with the parameter lambda sub I, and then sum of these random variables follows Poisson with the parameter sum of lambda sub I. Well, so we have supplement 1 to supplement 3. So can we use the previous result to prove this? Well, this one actually no. We should have a different approach. To have a different approach, actually we should have Z transform. And this Z transform actually will have the so-called generating function. Alright, so right now we have a Z transform or the so-called generating function. And then it can be proven if we have I independent random variable, then generating function or Z transform here, it should be product form. Alright, so we can follow some of the known results based on generating functions or the so-called Z transform, and also the fact if we have independent random variable, then the generating function or Z transform should be the product form of the individual one. Therefore, we can check, if we have the binomial random variable, what is the generating function? Binomial, the generating function follows the form here. It's pt plus 1 minus p and raised power to n sub I. So independent, we have the first one, second one to the nth one, and we have the common term. The common term still remain, and apply the product form to collect the exponents, and so that we still have the same form. All the exponents still have the form of the generating function of a binomial. So that's why if we have this idea, generating function for for binomial random variable follow this form, raised power to n sub I, and then here we can reach, we have the same generating function. So that says we have the binomial distribution. So Z transform or binomial probability generating function of binomial. So we have this. This is the first one. And the second one, if we have a negative binomial, what is the... This is a negative binomial. So actually, negative binomial, we have we have some form of probability generating function for sure. And likewise, we can have that one, but currently we don't show you exactly. Still, we will have the similar idea, and so that for negative binomial, we can find the corresponding form, and so that we have the negative binomial, sum of negative binomial still follow negative binomial. Well, again, so let me check probability generating function here. So it's Z transform form. Alright, but we call probability generating function. And let us look at the next one. So for negative binomial, we have the result negative binomial like this. Alright, alpha I, but follow the common form. And because alpha I different only, so finally we can collect here common term but sum of alpha I. So please see identical, we have the same PGF. And likewise, we can follow the similar approach to prove Poisson. And you can follow the definition of the probability generating function. So you can have the form for Poisson and product form for the generating function of Poisson. So finally, you can have a form follow Poisson again, but we have the rate. It's sum of all the rates. Alright, so this is the first one. The first one actually, it cannot be covered by our previous supplement, supplement 1, 2, 3. In fact, we should have a different approach based on Z transform or probability generating function. And then we can prove. So finally, we will have the result. Let me erase all and review the results again. Oh, binomial distribution, negative binomial distribution, Poisson distribution. For independent random variables, some of them for binomial common P but different n sub I. Negative binomial common P but different alpha I. And then we have sum of alpha I and common parameter, sum of n sub I common parameter. However, for Poisson, only the rate, different rate, sum of the rate forms the parameter of the resultant sum of the random variables. This is the first one. Okay, and the second one, if we have a random variable, follow here, it's normal. Normal random variable with mean and variance. Okay, and mean and variance, then if we have a function a plus by, so that says y equal to a plus bx. So this one actually we can follow a function of a random variable in supplement 1. Alright, so actually we can follow the formula or the way CDF first and then PDF. We can have the way to prove. Oh, okay. Finally, we still have a Poisson, but mean actually this one and variance. Well, I think all of you remember we have a property in chapter 4, how to have mean and variance of these. So mean here actually it's the individual one. Oh, okay, it's A and V. So of course it's A plus B, for example, mu. So even if we don't have the normal again, but we know the mean here. And about variance, actually we have a variance A plus BX. And this is a constant, so variance is 0. So 0 plus, and here we have a property B squared and variance of the individual X. So finally we have a BX sigma X. So B squared and sigma squared. So we have the variance. Therefore, this one can apply the results in supplement 1, and we can have the transformation. And before the transformation, I directly use the property to know mean and variance for the new random variable. But through the proof, it's normal again. So here we mention it's normal again, but we don't have the proof. I don't know the proof can follow the results in supplement 1. And right now, if we talk about this, how about mu and A sigma if N has the standard normal? Standard normal actually is normal with zero mean and unit variance. So of course, follow the previous idea, of course, how to have the results A plus B mu and B squared sigma squared. Alright, so this one actually we just let it have. Yeah, it's normal. Sorry, it's normal again. And this one, if we are given a normal density function or random variable x, so how about square? And this one same, supplement 1. And supplement 1 here. Okay, so if we have a normal, this is a PDF. And square actually can follow the form here to have a new PDF. And if we have this, follow the function, we can have these. And this one can have a form like this. And this one actually, it follows gamma random variable. So this one actually follows gamma random variable. But what's the form of a gamma? Alright, later we can check the form of a gamma. But in fact, we follow supplement 1, and this is a formula so that we can have the resultant PDF, and it follows gamma. But what's the gamma? So we can have the gamma density definition first. So we consider this one. Oh, okay, if we have a form like this and try to make this to a PDF, how to make it to a PDF? So we need to find a constant C. A constant C like this, and so that we can have the form. Alright, and for the form here, oh, okay, C can follow something like this way. So you can follow this way, but we define this one, gamma function. Alright, gamma function actually, oh, it's x raised power to alpha minus 1 and multiply exponential raised power to minus x, and the integral from 0 to infinity. This is the gamma function. And so that constant C here, because follow the gamma function, so we know C should have a form in terms of a gamma function. You see? Gamma function, and if we have a C like this, so we can have the gamma density follow the form here. Alright, so if we have a parameter lambda and parameter alpha, So this is a dummy variable x. So it says lambda raised power to alpha and over gamma function alpha, and the x raised power to alpha minus x, and exponential raised power to minus lambda x, and only for x greater than 0. As for the others, it's 0. So this form is gamma. Alright, so it's gamma, and actually for gamma function we have some special number. Gamma function, if we have gamma function equal to a half, and then we have the special value. Alright, and the special value, you can look up the special value, and this special value related to pi. Alright, so if so, yes, if we follow this gamma a half, and right now we have a result like this: sigma 1 over sigma square root of 2 pi y exponential raised power to minus y over 2 sigma square. Alright. So follow the current form. She looks like this. So we have 1, right? Look at this again. Here. Alright, so this is the PDF. And the PDF should follow a form like this. Even right now it's x, but right now we have a y, and y here we have minus a half. Alright, minus a half we can return in terms of this. So here we can have the exponent alpha. Alpha is equal to a half. Alright, so alpha equal to a half, and we still have lambda. And lambda x here, lambda x, lambda equal to right? So we have this, a half, and lambda equal to 2 sigma 1 over 2 sigma square. So look at this. Here, oh, it follows the form gamma random variable a half and 1 over 2 sigma square. So yes, we can find it. But I don't let you know, oh, the value, gamma a half. So gamma a half, if we want to find the value, actually we can have the value, but I just follow the current one to let you know, oh, okay, we have the form. Alright, it's a half. We have the form already. And right now, we have a parameter here. So is it true? We have a half. And then we have a gamma a half. And these are actually equal to these. Oh, okay. The remaining, it should be sigma and square root 2 pi. Alright, so let me use a different color. Here we have these. This one can be rewritten. Alright, so equal to this. So square root 2 Square root 2 cancel. Sigma cancel. So this one, oh, gamma have equal to square root pi. Alright, so actually you can look up, is it true? Gamma have actually, we have the results. And furthermore, you can prove based on the gamma density function, we have a property for gamma. Actually, alpha plus 1, even it is not an integer, we will have alpha and multiply gamma alpha. Alright, so this is a recursive formula. You can check it, is it true? And this is the gamma function and gamma density function. So let us rewrite. Here we have the gamma density function, and this is the gamma function. This is the gamma density function. Alright, so you should have the way to distinguish gamma function and gamma density. Yeah, it's true, gamma density function. Alright, so gamma density, we have lambda alpha over gamma of alpha, and the x raised power to alpha minus 1, and the exponential raised power to lambda x. Only for x greater than 0, and 0 for the others. So this is the gamma density function. Alright, as for gamma function, alpha raised power to alpha x raised power to alpha minus 1 multiply exponential raised power to minus s, and through integral from 0 to infinity, the value is equal to gamma of alpha. Well, this is the results here. So we have results. Oh, okay. If we have a normal zero mean and sigma square, and talking about x square, then we have the final random variable follows gamma with the parameter. Here it should be position for alpha, and this is position for lambda. It should be a half and 1 over 2 sigma square. So this is the property. And next one, this one actually related to supplement 2. We have 2 random variables. Sum of 2 random variables. Alright, but right now not 2 only, we can have n. So we can try how about 2 first, and then using the extension. Alright, so if we have gamma alpha sub I and common parameter lambda, then independent random variable, sum of independent random variable, then we have a gamma again, and we have a sum of parameter alpha and common parameter lambda. So we can apply results in supplement 2 to prove it. Oh, okay, this one follows gamma again, and so we can have the proof using induction, mathematical induction to prove. Oh, okay, so 3 here follow gamma again, so gamma again, so we can use mathematical induction to have the proof. Alright, so for this one I mentioned yes we can prove it, but I don't mention in detail, and that okay, that's it. And this one talking about independent random variable, this time it's normal. Normal we can have mean and variance, and some of these still normal, so sum of mean and sum of variance. Again, we can have the results in supplement 2, and we can prove, oh, okay, it's true. And likewise, we can use property. Oh, okay, property of this, yeah, so we have summation, And the variance we have a summation because of independence. So it's true. Even we don't know, we still follow normal random variable, but we can know, oh, okay, mean and variance follow the relationship. Okay, this one, it's simple by definition. In fact, we can have a chi square with a degree of freedom n. Actually, this one identical to gamma with a parameter n over 2. It's alpha position and a half. So this is, you can think this is a relationship and serving as the definition for chi square. So chi square is a special case of a gamma with a parameter n over 2, but here n serving as the degree of freedom. Alright, and the next one, lambda, is a half. Well, so look at this. We can consider a special example. If we have this, here, this one actually it's zero mean, and with variance sigma square. If we have the assumption then about this, x sub 1 over sigma, what's the distribution? It's the standard normal. So standard normal, it says we have zero mean and univariance is normal. Oh, okay. So here we have standard normal. Alright, so previously standard normal, so we have this square, so we have a half, and this one sigma square is 1. So we have a half and a half. And right now, sum of n gamma, so we have n. So finally, we have the results. So of course, this one follows chi square with a degree of freedom n. So this one, we have some description based on the previous property. And then we can show, oh, okay, it's true. Yes, it follows chi square. And actually, in our supplement previously, we have some possible description, including chi square. You can check it. Is it true? And this time, this one also follows something like it's a definition. But definition says, okay, we have chi square degree of freedom k sub 1, k sub 2, and ratio. And this one we call it's the F distribution, k sub 1 and k sub 2. So this is a definition. And I skip it directly. Actually, if so, then we can have the previous description. Oh, okay, all of these follows normal, zero mean, and the sigma square. And it asks us to think about this. So what's the distribution? Actually, it's the F. You can check it. And I skip the description. You can check it. And again, this is a definition. If we have y sub 1 and y sub 2, and follows standard normal. And the chi square with the degree of freedom k. So standard normal over the chi square, and the chi square over its degree of freedom, and this form we call T distribution. The random variable follow T distribution with the degree of freedom k. So this is a definition. And same this one. Oh, okay, if we still follow previously, oh, x follows the normal zero mean with sigma square. And then the form here actually follow, we can have over sigma again. So we can have x1 over sigma and return all of these. So x2 square plus the other plus xn square and over sigma square over n minus 1. So here standard normal, and here standard normal, we have square of the standard normal, we have n minus 1. So sum of n minus 1, we should follow chi-square with a degree of freedom n minus 1. And over its degree of freedom, so of course here is t distribution with a degree of freedom n minus 1. Alright, so this is the possible extension. Well, actually, we already have some actual result, that we have some actual definition. And finally, this one, it is related to some results in our content in chapter 4. And actually, this result can help us to know why. But let me have the results here. Alright, so assume x sub I follows normal density function with mean mu and variance sigma square. They are IID. Alright. Okay, so if we have these, and then we have variable x minus its sample mean. Alright. And raise power to 2 and get the sum over sigma square, and we have the variable denoted by w sub 2. And this one, it is a chi-square random variable with a degree of freedom n minus 1. Why is it true? So if we want to prove this, then we have the following step. We need to go through and prove it. And for this, actually, how to prove it, we have many steps. Let us try one by one. So first of all, we have W. Alright, so W actually, we have a really simple one. It's x sub I minus its mean and over sigma. So if this one, x sub I, follows normal with mean and sigma. So this one, previously we didn't know, this is the linear function. And finally, what is the distribution? Oh, it's normal again. But what is the mean? Okay, so mean we cannot know. Oh, okay, just the manipulation. So originally it's mu minus mu and so phi over sigma, so it's 0 mean, and variance actually it should be, oh, this one constant, no, and so that we have a sigma 1 over sigma square, so sigma square itself, so it's 1. So here this one actually follow normal, 0 mean, and univariance. So if we have this raised power to square, so this one raised power to square, so it should follow, oh, it's one over 2, and the square, so 1 over 2. And right now we have the individual one follow this sum chi-square, so we have n, so finally we have n terms. So finally we should have another property. Oh, we have parameter sum of alpha, so it's n. So finally it's chi-square with a degree of freedom n. Yeah, it's true. So step 1, I think, follow some property and we can prove it. Alright, so this is the first one. And the second one, we have sample mean itself minus its mean and over sigma square, but multiply n. So this one we can rewritten, and so that it's x bar minus mean and over sigma square over n. Alright, so here it should be square, so it should be square. Look at this. In chapter 4, mean of this is equal to mu again. and variance of sample mean, it should be sigma squared over n. Alright, so if we have this, we also know, if we have the variable minus its mean and over its standard, it's the standard deviation. This one follows uniform with a zero mean and univariance. And right now, square. So because of a square, so that we should have chi-square of a half and a half. Previously, we've proven this. So it's a degree of freedom 1. So yes, it's degree of freedom 1. All right, so right now we reach step 2. And finally, we have a step 3. We assume, y1 is the sample mean. And y2 is the statistic x2 minus sample mean. Y statistic minus the sample mean, that says minus y sub 1. And so that if we have the definition, we can derive variable as follows. Okay, so x1 actually can be expressed in terms of y1 minus y2 to yn. And x2, it's y1 plus y2. And xn, it's y1 plus yn. So for this y1, so xn equal to this, x2 equal to this. It's easy. Right? So we can have x2 to xn follow the form. It should be y1 plus yn, y1 plus yi. For summation I equal to 2, and we can have the result to n. So y1 plus yi. So here this is summation. So if we have x1, so sample mean actually equal to y1, right? And this one, so it's y1. So finally we have ny1 equal to x1, and summation y1 plus yi. So here we have n minus 1, y1. So cancel these. So x1 actually equal to y1 minus summation of yi, I from 2 to n. So that's why we have this variable. Alright, so actually we can have the definition in step 3, and finally we can have the derivation for variable in terms of x sub I. So we can have step 4. Once we have step 4, then we can follow step 5 to write. Previously we have W2. By definition, follow this, right? And follow this, we can rewrite. Alright, so x sub I, here, x sub I equal to, if I greater than or equal to 2, we have y1 plus yi, and y1 actually equal to sample mean. Alright, so for this actually we can have this. Here we have x. Actually, we can have the way to rewrite. So we have this one. So let me erase some and then let me continue. So we have x sub I minus this. So we can have second one to the nth one, the individual one for the first one. And x1 minus x bar. this one. X bar. So we have the result. It's the summation from 2 to n of y sub I. And for the first one, actually this one here, we have this one, we have xi equal to y1 plus yi. And this one is x bar. So xi minus x bar equal to yi squared. Alright, so W2 actually related to y2 to yn only. Alright, so this one actually just when we write the form, and actually we can reach the form here. It's step 5. And step 6. Alright, step 6 actually we can have the results. X sub I minus mu. So here we have the result, not over sigma squared. But we want to rewrite, okay, same, we can minus x bar and plus x bar. And minus is mu. And we can expand. So this one we can rewrite. Actually, it follows the equalities. This one and this one. Once we have the way, okay, so data check, we have the join PDF. And join PDF, actually, we can have the results. Okay, it's x1 and x2, and we have the Jacobian. All right, and actually, you can check Jacobian equal to this. All right, previously we don't check, but actually we have a Jacobian equal to n. So we can multiply, and this is the individual y1 to yn, and x1 and x2, they follows normal. So here we have a normal. Alright, so we should have the form normal, but multiply n. So currently, let me stop here and rewrite. So normal, join normal. So we have the independent normal. Alright. So actually, for some scalar, we should rewrite. Alright, but actually it's true for the term. So for the constant, maybe we need to rewrite. But I still think, okay, you can know how to correct. But let me check and continue. And this one, why we want to have the form here? Because we want to replace this one. And replace this one, so we can rewrite. For this one, n is a constant. This one should be corrected, but I skip that one. Focus on this. Okay, if so, then of the form here, it can be yi squared, and here yi squared, and multiply the individual one. So we just want to pull. Okay, so join PDF, actually it's a term of y2 to y1 and y1. Sorry, y2 to yn and y1. So it's a product form. Product form, so it says y1 and the remaining, they are independent. Alright, so for the step here, we can apply the results, the formula in supplement 3, and we can have the independence, proof of the independence. If we can prove of independence, then we know, okay, so W2 actually y2 to y1 related. And W1 is Y1 related. So, of course, W1 and W2, they are independent. If they are independent, then finally, they'll have the final steps. Step 8. Okay. W here. actually you can write as this, and through the manipulation actually you can reach. Alright, so it's sum of W1 plus W2. You can check all the details here, and they are independent. So this is a distribution chi-square of chi-square degree of freedom n, and this is a chi-square degree of freedom 1. And if we want to have the chi-square and follow the previous property, chi-square is gamma. So this one should be gamma again, and n minus 1 and a half. And so that sum follows the degree of freedom of n. So if I want to follow that property, that says only for W2, it follows chi-square with this degree gamma of this, and says it's chi-square n minus 1, and then we can meet the current steps. Oh, because of that, so finally we can reach the results. Oh, this one actually it follows chi-square with the degree of freedom n minus 1. So we can follow the A step to prove this fact. Well, and currently this one, so how we correct? It should be this one. So we have n times, so we should have this. This one should be n. Alright, and this is a correction. So finally, let me erase all. So how to have the correction? All these, it should be n again. And then that's all. So even I have a typo for the current derivation, but it doesn't matter. We just want to have the separation so that we have y2 to yn and the y1, and then we have the results y1 and the remaining y sub I, that says from 2 to n, they are independent, because we just want to know, oh, w sub 1 and w sub 2, they are independent, just for this purpose. Alright, so this is the step, a step to prove the results. Let me erase all. This one, w sub 2 follows chi-square with a degree of freedom n minus 1. Alright, that's all. These are all results provided in supplement 4, and actually I have some reasonable way to explain or maybe to prove, and hopefully you can understand, or of course you can practice more, and so that you can know more about these useful results. Alright, that's all, and see you next time. Bye bye.